Hey everyone, welcome. So today, in this explainer, we are going to completely demystify something that literally revolutionized the entire coding world in computer engineering. We're talking about the core logic of object-oriented programming, or OOP, in its absolute simplest form. Whether you're a beginner programmer, just trying to wrap your head around the basics, or you're looking to brush up on your skills before midterms, consider this your ultimate study guide to crushing your exams. We're going to break down the 4 foundational pillars of OOP using actual, real-world code examples. Okay, let's dive right into it. Now, before we even get into the nitty-gritty, let's tackle a question I hear all the time. Like, why don't we just write a bunch of top-down functions and call it a day? It's a completely fair question, right? And hey, procedural programming is great for really small tasks. But when it comes to modeling the complex, real-world, and software engineering, top-down functions just don't cut it. The real world isn't some rigid list of instructions, it's a massive collection of interacting objects. OOP actually gives us the tools to map our code directly to the real world.
So here's our game plan for today. We'll kick things off with a quick intro to the OOP world and then systematically conquer the 4 big question types you'll see: classes, encapsulation, inheritance, and polymorphism. Finally, we'll look at exactly why OOP is the absolute industry standard.
All right, let's jump straight into Section 1, an intro to the OOP world in our first pillar, classes.
Okay, pretty much every OOP exam is going to test you on these 2 fundamental terms, class and object. Think of a class as basically your blueprint or template. It defines the properties, which are just your variables, and the behaviors, which are your functions or methods. An object, on the flip side, is the concrete actual instance that is created from that blueprint.
Let's put that into perspective. Imagine a car factory. The class is just the drawing, the blueprint. It tells us that a car should have a brand, a model, and the ability to accelerate. But, you can't drive a blueprint. The actual car, the object, is the physical vehicle that actually rolled off the assembly line. So the class is the plan, and the object is the reality.
All right, listen closely because I'm putting on my professor's trap hat for a second. This specific question, it is practically guaranteed to show up on your midterm. You'll be given a Python snippet and asked, what is the exact purpose of the init function?
Take a look at the code. See how the car class uses an init method taking in brand and model as parameters? Well, its exact purpose is to act as an initiator or a constructor. It is automatically called the very moment an object is created to give that object its initial state. Basically, if you want your car to have a brand the exact second it rolls out of the factory, it absolutely has to go in the init method.
Moving right along to Section 2, in question type 2, encapsulation.
So what is encapsulation? Well, it's essentially the security system of our code. It means we restrict direct access to an object's internal data, and we only allow outside code to view or modify that data through specific, highly controlled methods. We are basically hiding the complex internal state and protecting it from unwanted interference.
Think of it like this. Leaving your variables completely open is like having an open safe sitting in the middle of a room where anyone can just walk up and grab cash. Any part of your program could accidentally change crucial data. Instead, we use encapsulation. You talk to a bank teller, which represents a method, who safely processes your request. We never, ever let outside code touch our internal variables directly.
Okay, time for another classic professor's trap pulled straight from our source material. Imagine you're looking at a class that flat out refuses to let you grab the brand variable directly. Instead, it forces you to call a specific method just to return the car's information. What concept is being demonstrated here? And the answer is encapsulation, or kapsaleme if you're taking this in Turkish, because that data is completely tucked away, forcing you to use the car info method to access it. You're seeing data hiding in action. On your exams, if you see methods acting as gatekeepers to hidden variables, your brain should immediately scream encapsulation.
All right, let's hit Section 3, question type 3, inheritance.
I actually like to think of inheritance as the art of being lazy, but, in a highly efficient, smart way. Inheritance is a mechanism where a new child class automatically takes on the properties and behaviors of an existing parent class. It's exactly like passing down genetic traits, but in your code. You write the functions once in a parent class, and the child classes just inherit them for free.
For example, take a generic animal class. That's our parent. Let's say it has a name and it makes a sound. Now look at a specific bird class, the child. The bird automatically gets the name and the sound from the animal parent, but then it adds its own unique feature, a wingspan. We didn't have to rewrite any of that original code, we just inherited it.
So, here's how they'll test you on this. You might get a multiple-choice question asking for the foundational reason behind this structure, like why exactly does the bird class inherit from the animal class in this specific Python snippet? Let's break down the solution. If you look closely at how the bird is defined with animal in the parentheses, and specifically that super init line, well, that super function is literally the magic keyword here. It explicitly calls the parent's traits. The bird class inherits all properties and methods from the animal class, which completely prevents code duplication. Let's move to section 4, question type 4, polymorphism.
The word polymorphism literally just means many forms. In the OOP world, and specifically when we're talking about method overriding, it means different objects can utilize the exact same method name but behave in their own unique, highly specific ways. It's what allows us to write general code that works seamlessly across a bunch of different types of objects.
Okay, get ready, because this is a classic output prediction question. They love these on exams because it tests if you actually understand how overriding works in practice. If a generic animal class has a method returning making sound, but a dog child class overrides that exact same method, what happens when we specifically call the dog sound method?
So what happens? Well, the dog class has its very own sound method that returns hav hav, which, fun fact, is exacting how dogs bark in our Turkish source code example. When we ask the dog object to make a sound, the final output is hav hav. Python looks at the actual object type, sees it's a dog, and uses the dog's unique overriding behavior instead of the generic animal sound.
And finally, section 6. Why should we even use OOP? If you look at the old way, procedural programming, the code is entirely function-based, the data is separated, and honestly, the scalability is pretty low. If you try to build a massive app this way, it quickly becomes a tangled mess. OOP, on the other hand, is object-based, the data is cleanly encapsulated, and it offers incredibly high scalability for really complex, evolving projects.
So, to sum the whole shebang up, OP drastically reduces code repetition. It provides a clean, organized structure, and it makes huge, multi-developer projects actually manageable by modeling the real world accurately. You've mastered the 4 pillars now, and you know exactly how to crack the exam logic. But honestly, passing the test is just day 1. The real question is, now that you hold the blueprints to build literally anything in the digital world, what are you going to create first? Thanks so much for joining me today.